Okay, hey.
Okay, Anubhav, is that you?
Yes, sir.
Okay. Anybody else? Then Anubhav is answering most of the questions. So anybody else should try. I mean, they should unmute themselves and tell me what answers you are getting. Or else there is no use of this live session. I mean, if you don't interact, then the entire thing is a waste. You can take a book and solve the sums by your own. Anybody else who has done the sum? What about Divyajyoti Shahu? Have you done? Have you tried the sum? Hello, am I audible?
I'm already just copy and first time in the class.
Yes.
This is my first class, sir.
This is your first class. Okay. So,
Yes, sir.
so I mean, did you know how we are what we are doing over here and how we are proceeding? The thing is that we are expecting that you have covered almost the syllabus and you are here to practice sums. So I would expect you to try and solve the sums that I'm giving you because of
Yes, sir. Tomorrow also I will practice. Revision topic first.
okay. And you are from which year?
I'm 21. Password.
You are
21 password.
you are pass out. Okay,
Yes,
okay,
sir.
okay. So okay, so let us go ahead with the solution because Anubhav has already said. So Anubhav is saying answer A. I mean the option A. So let us say it is very easy question. So first you have to find the route array for it. So if you find the route array, you will find that you have a element 6 minus k divided by 3 and another element k. So for all the roots of the equation, the roots of the characteristic polynomial to be on the left hand side of this plane, all the coefficients, all the elements of this first column should be positive. So k has to be positive, that is k has to be greater than 0, and 6 minus k must also be greater than 0. So k must lie between 0 and 6. So the answer is A. Okay, so it is simple and all, everything is okay, but let me ask you a few questions from here to get a better insight. Anubhav, you have solved this sum, right?
Yes, sir.
So tell me, this route array can tell me everything about the stability of the system, right? Because to determine the stability, what information we need to know is to ensure that all the closed loop poles lie on the left hand side of the S-plane. That is all the information that we need to know. We do not need to know the exact location of the poles. This much information is enough for us, right?
Yes, sir.
So route array, I mean, so what is the need for any other method? I mean, why did then Nyquist plot came into the the Nyquist stability criteria and all those came into the scenario? Is route array enough, or is there something which route array is missing? What do you think?
सर सर पोल्स को देख के भी बता सकते हैं स्टेबिलिटी नाइकिस्ट से
Yes.
we can judge stability by seeing the number of poles and views from Nyquist criteria.
No, I am asking that same information is given to you by route array also. What is the need of Nyquist criteria? If route array is telling you how many poles, closed loop poles are lying on the left hand side of S plane, then why do you need Nyquist criteria?
Sorry, sir, I am unable to recall.
Okay, anybody else who wants to participate in the discussion? Chaitanya?
Sir, maybe it is for minimum phase systems like for minimum phase transfer functions.
Minimum phase transfer function. So what do you mean by what do you are trying to say? I mean,
I mean, I have actually studied it in somewhere, like, but
Yes, Chaitanya, please
like,
continue. Yeah.
yeah, just one moment.
Transfer function.
What transfer function?
Can I get in transfer function?
Please, Gangadhar, please mute yourself. I will come to you.
Okay, sir.
Yeah, Chaitanya. What were you saying?
Yes,
Please repeat. Yes.
yeah. Actually, like for example, for LTI systems which are inverse, I mean, which are causal for those particular systems,
Mm-hmm.
uh, it may not be suitable. I mean, it is suitable only for minimum phase systems.
What is suitable for LTI system?
I mean, root array or Bode plot. From those things, we can find stability for those functions. But
Now see, you
next,
are saying that for non-minimum phase systems, Bode plot cannot be used. That is not true. You have to, if there is a non-minimum phase system, there is a way by which you can use it for analyzing non-minimum phase system also. How you will do it? There lies the trick. What you have to do, there is something called Blaschke product. You have to, you will know this when
okay,
you go for higher studies. So it is a wrong notion that people have that for non-minimum phase systems we cannot use Bode plot. You can use it, but you have to have that adequate knowledge how to use it. So Bode plot is mainly used for design perspective, for for getting the performance criteria that has been given to you by your employer. Say your employer has told you ki you need to have this much of steady state error, you need to have this much of disturbance rejection, you need to have this much of at this frequency you need to track the signal. So those for those specification, for those performance specifications, for designing of the controller you need Bode plot. Okay, right.
okay,
And how, I mean, these things is not that much required for gate. I know that for gate what you need to do is you to practice sums, but just to have an insight, because only doing sums is just like a mechanical stuff going on. So I thought a bit of discussion would be good. So the thing is,
sure,
you see, one thing, in case of route array, the problem that you see is, see, this equation that you see is the mathematical model of the physical plant that you have, right? Say you have some kind of a, say, kind of a boost converter, a buck converter, or maybe some mechanical system, maybe a spin damper system, and what you are doing is you are writing a mathematical equation for modeling the physical system that you have, right? Chaitanya, you are getting me what I am trying to say?
yes, sir.
Yes. So you see one thing, this route array is very much dependent on its coefficients, 3, 2, k. So your modeling has to be absolutely exact. Okay, but in real world, then you see this coefficient may not be constant. It may be varying with time, it may be varying with temperature. So this coefficient, it may so happen that these coefficients are, there is uncertainty in this coefficient. You do not know exactly what these coefficients are, and in that case, route array may not be a very good option for you to, determining the stability of the system. Somebody a few minutes ago wrote about relative stability. There is a way to, to determine relative stability here also. If you shift the origin, the s plus a or s minus a, you can say, I mean, whether it is relatively stable than others. So relative stability is not the issue. The issue over here is the coefficient. It is very much dependent on this coefficient. It may be time dependent, or it may not be modeled by us correctly. So in that case, the route array is not going to help you at all. Whereas, if you understand the philosophy of Nyquist plot, in which case what you do is you encircle the entire right hand side of the S plane. Okay, so if you are encircling the entire right hand side of the S plane, then you can, whatever be the coefficients, then it gives you, the the criteria will tell you, how many closed loop poles may lie on the right hand side of the S plane. So it helps you in that fashion. So that is why Nyquist came up with that criteria. One day I think maybe in the future class I will take one class on Nyquist criteria. I will discuss and I will tell you what the basic philosophy of Nyquist criteria is. But right now, because I too have some exams, so I'm not getting much time to prepare all these notes. Okay, so I have to prepare. It takes a lot of time for writing all these equations and editing all these videos and all. But yeah, I do really wish to teach you Nyquist criteria to you once. Let me see if I find time. I will do that. Anyways, so is it clear to everybody why we go for this route array? Is it? I mean, how is Nyquist criteria helpful and is sometimes better than route array?
Yes, route array is coefficient dependent.
Yeah, I mean you have to model your plan exactly. I mean it may so happen your plan has certain uncertainties. It may not be modeled so accurately. In that case, you cannot write a characteristic equation with 100% certainty. So in that case you land up in trouble. Okay, so I would let's see whether I can ask you. I will ask you another question, but before that let us do another sum and then I will ask you. Okay, so this is another sum from 2015 GATE paper. So in this question, open loop control system response, impulse response of open loop control system has been given to you. That is e whole to the power minus 2t sine 5t plus cos t, and you are asked to find the DC gain of the control system. So try it. I will give you 3 minutes time to solve it, and then we will discuss. By the time you practice, let me talk with Gangadhar. Gangadhar was asking something. Gangadhar, what were you asking?
Sir, transfer function.
What do you mean? You want to
Transfer
discuss
function can
transfer
explain,
function?
sir. Transfer function, sir. Can explain a transfer
Yes,
function.
transfer function is defined as the Laplace transform of the output divided by Laplace transform of the input, assuming initial conditions is equal to 0. This is what transfer function is. What do you want to know about transfer function?
Yes, sir. Yes, sir. Sir, can solve this sum only. This sum, sir, can solve.
Which sum do you want to solve?
And open loop control systems result in the response of e power minus 2t into
I will
sine.
discuss the solution. As of now, I am giving time for other students to solve the question. Those
Yes,
who
sir. Can
So I have given time
can,
for them to solve the question. Let me see how many people can answer the question. Then I am discussing the solution.
yes, sir. Can solve, sir. This sum on.
You can mute yourself because I mean I most of the times I don't understand what you are asking for. You can mute yourself because background noise disturbs us.
Sir, we will try.
Yes.
The
Anybody
point
else
two
can answer? Yes.
point 241.
Yeah. Yes. Okay. Anybody else other than Anubhav who has solved the sum? Chaitanya, have you tried?
No, sir. I was actually in journey.
Okay. Okay. Okay, so if I hope people are trying, I hope that you're not just seeing what I'm doing. Uh, so actually, it puts I actually spend a lot of time preparing all this stuff. I hope that you people try all these things. Anyways, so how to find the DC gain of the control system? You see, the impulse response has been given to you, but it is given in the form of it is given in time domain. So to find DC gain, what do you mean by DC gain? That means what is the gain that the system is providing when I am inputting a DC signal to it. That is what DC gain of a control system means. That means if I can find a frequency response of the system whose impulse response has been given to me and then substitute omega with equal to 0, then it will give me what gain it produces for a DC input. So let us do that and let us see what we get. So the impulse response that I have written over here is ht to the power minus 2 is given in the question. I am taking the Laplace transform of the expression. So what do you get? That is, so if you do the Laplace transform, you will end up getting this expression. And to find the DC gain, as I have told you, we have to put s equal to 0, and if you do that, we end up getting 0.4137. So this is how you solve this sum. Okay, so this was a basic question. Let me go for the next question. My quiz plot is there. Okay, let me go to it a bit later. Okay, let me ask you some other question. I have prepared some document for discussion. Let me see. Okay, I would be asking a very basic question now. Let me see whether you can answer all this stuff. Okay, so tell me first of all, what is the motive behind using all these control systems and all? What is the basic funda behind all this? Anubhav, why do you, what is the main purpose behind all these things that we are studying? What is the motive behind studying all these transfer functions, doing all this study, stability studies, and then Bode plot and root locus? So what is the main purpose of doing all these things? What are we actually trying to achieve? Anubhav?
We try to make our system stable.
No, that is not our primary objective. That is not the primary objective of a control engineer to get a stable system. It has to do something. It has to perform something.
To
I'm asking you,
command.
what do you want as a control engineer for the system to perform?
Mathematical model of the system.
No, mathematical modeling of a plant, you have to design the controller. You are saying designing a system. Designing a controller is the work of a control engineer. It is not designing a plant. So you have a plant, and what you actually want is, you want the plant to follow your command. That is your main objective of a control system. That I am giving a command xt, I am getting an output yt. What I want is yt must be equal to xt. That is what my objective is. And all this feedback and all this theory that you study, that was developed back when all these landline telephones were there. Back in those days, the feedback concept, the feedback loop concept was discovered by somebody named H.S. Black, and he gave the solution to a several problem that we will discuss today. So you see, say xt is a signal that I want to transmit to somebody maybe far away from me. I want to transmit. So while transmitting, it is getting attenuated by 1 by k0, and then what I am doing is I am amplifying it and I am sending it to yt. So if I design a system like this, then I am sure to get yt equal to xt, right? Then what was the need for all this control, all this closed loop and all? Anybody from the audience? If Anubhav, what was the need for all this feedback system there? Yes. Yes. I cannot understand what you are saying.
Can I explain, sir?
What will I explain? You are always asking, what do you want me to explain? I am asking you a question. You have to answer what the question I am asking. I am asking you, what was the need for all this feedback loop and all? If I can get yt equal to xt by doing this operation, then what was the need for all this feedback loop?
Feedback? Yeah. Hello?
Yes, Anubhav, I am listening.
Sir, feedback to check our output constantly and adjust our input accordingly so as to control the.
Ganga sir, why are you not muting yourself? Yes, Anubhav, yeah, tell me.
Yeah, so we use feedback to check our output continuously and change input accordingly so as to get desired output.
See,
Like,
so say if I change the input over here xt, okay, and if it is passing through this system 1 by k0 and multiplying with k0, then it is okay. Then yt becomes again equal to xt in spite of whatever disturbance we have over here, right? If I have a disturbance at this input, I mean maybe if I want to track this signal, if I'm giving a signal which I want my system to track. So say suppose I change my reference input. So first it was 1 volt, now I have changed it to 5 volt. So according to this, this figure that I'm showing, then yt will again be 5 volt. Then what is the problem with this?
generally in transmission, uh, there are a lot of noises are coming through. We change the amplitude or frequency accordingly. That is modulation.
Noise at what point? Where are you seeing the noise over here? At which point? Over here? Over here? Over here? Where?
Or transmission.
Over here.
No, in between.
In between noise.
Yeah.
Okay. Any other
In the
reason?
plant. Yes.
Yes. Yes. Tell me.
Yes.
Yes. Whoever was trying to answer.
Good explanation.
Yes. Anybody else? Abhishek? Abhishek Sharma?
Carry on, then carry on. Next question.
Gangadhar, if you don't mute yourself, okay, I will just remove you from the meeting. I'm telling you for the last time. I do this every meeting, and you are doing this every meeting. This is not acceptable over here. Anyways, Abhishek, I was asking you, can you tell me what was actually the need for all this feedback and all? Chaitanya? Chaitanya, am I audible? Are you able to hear me?
Yes, sir.
Chaitanya, can you please, try to answer the question that I'm posing to you?
Just a moment, sir.
Yes.
Just a second.
Yes.
Yeah.
Yes. What
Sir,
I'm asking is, yeah, tell me, yeah.
yeah, actually, like we use those feedback systems, like to adjust the output for reducing the errors, sir.
For?
I mean, to adjust, we are using these feedback systems, for example, to adjust the output, to adjust according to our required output, and minimize the errors, reduce the errors.
Yeah. So Chaitanya, my question is, say I want to
Sure.
adjust the output according to my input. Okay. So
Yeah.
say I have changed my input from 1 volt to 5 volt. According to the operation shown by this block, then yt becomes equal to xt, right? Then
Yeah.
whatever change I make in xt, yt would also follow the same. Then what is then open loop systems is good enough. What is the need for closed loop system? Are you getting my question?
Yeah. Okay. With respect to this system, I mean 1 by k naught and k naught,
Yes.
then in this case we may not be required, sir. It depends upon the system which we are giving the input.
in case any error comes in input signal, so that error will be transmitted to output. But if feedback is present, we
If
are
feedback is
continuously.
present, if any error comes in the input, then that will also come in output.
But
That you
we
cannot
can
change.
adjust the input accordingly so as to eliminate
Otherwise
that error.
disturbance, right? So whatever disturbance is coming in the input, that is not that is something that you cannot control. So if there is a disturbance at this port, then you have no control. Then there is a problem. Then your YT will always track XT. That is also true for any system also. Then what is the need for all this studying all this feedback, and why did people come up with feedback? Anybody else try to answer, try to think. Divyajati, I am asking a very basic question. You can try and ask. You try and answer.
Compare the output with the reference input.
Compare the output with the reference. So what is the need when I am giving a reference input over here and I am getting whatever is the reference input? Then what is the need of comparing? Because these two blocks are making sure that xt becomes equal to yt. Then what was the need for comparing this with this?
For minimizing the error.
This is see, if yt equal to xt, then error is 0. What is error? Error means reference minus output.
Reference minus.
So if according to this operation yt is equal to xt, then what was the need for all this feedback? This is the fundamental question which should be asked to every student who is taking up control system. This is the fundamental question. Why did this feedback system at all come into existence? Why did people think about feedback system? Feedback system was invented by H.S. Black during those days when telephones were there. Because you transmit a signal and that used to get attenuated, and what you do on the receiving end, you use some kind of amplifier to amplify it and then send it to the receiver. That is what we used to do. Now question is, why did H.S. Black thought of some feedback or something? Why did he came up with this idea of feedback? That is my question to you. Anybody else want to try? Anybody else? Jeevan, if you are in the meeting, you can try and answer. Raj, are you there in the meeting?
Yes, sir.
Yes, can you try to answer what the question that I've asked?
Actually, if we compare the reference input with the output, if the output is deviated from the after our reference input to minimize the error and to send the reference signal to control the reference input, we use feedback.
So everyone is I am answering the same thing. What I am saying, see, if the system is somewhat like this, 1 by k0, and I'm multiplying with k0, then the error will automatically become 0, right? Then what was the need for
Like,
comparing and making systems complex?
yeah, I mean to make the input go faster. I mean,
Faster?
by reducing.
Faster than open loop? How would it be faster than open loop? You are sending some signal from here to here. That will take some time to go over here, and then something would happen, and then you will get something output. How would it be faster?
Sir, the blocks are like a plant or process. In the plant or process, some external noise can be introduced to avoid
Noise,
the.
yeah, noise has been told by Anubhav. Anything other than that? See, noise is one issue, but there is far greater issue than that. The greater issue that I am talking about over here is the main purpose that you do, that the reason why you do Bode plot, root locus, and Nyquist plot, everything are linked with all these things. So that is why I'm asking a very fundamental question. Just a minute. So I'm asking a very fundamental question. That's why. So why did we go for this system? That is my question. So the problem that because we have a limited time, let me tell you the problem that H.S. Black faced. The problem over here is this amplifier, the amplifier which used to provide the gain to the signal at the receiving side, is not reliable. This factor k, this factor k varies to a great extent. It can vary from 10 and go up to 2, so it can vary by a factor of 5. Okay, in such a case you see the error would be around 80% when there is uncertainty in the gain of the plant that we are talking about. If there is uncertainty, see this I have fixed on the transmitting side 1 by k0. This gain I have designed such that this gain is 1 by k0. But this over here, used to create a problem. This amplifier gain back in those days was not very, reliable. So if you are using the same batch of amplifiers, then also you will find that even if it's mentioned 10, it can go as low as 2 or something like that. So say suppose k0 is 10 and it goes by a factor of 2, then you will see the error goes about 80% error you are getting. You are getting my point, right? You are getting my point, right, everybody?
Yes, sir. Yes, sir.
Yes. So H.S. Black said that okay, if this is the problem, let us do something to the system. So what he did is this. So over here, what you see is, over here you see there is a gain k, and then yt becomes equal to k0 divided by 1 plus k0 into xt. So if you can ensure, you do not know what k0 is, you may not know what k0 is, but if you can design something and place some block over here and ensure that this gain, maybe I've lumped this entire gain as k0, the controller gain and the gain of the plant as k0. In such a case, if you can ensure that k0 is large enough, then what happens? Then 1 can be neglected. So yt becomes equal to k0 divided by k0 into xt. So you get yt equal to xt. So you need not know what k0 is. There need not be any certainty of the value of k0. It may be uncertain, but if you can ensure that if k0 is large, then your error, then your yt becomes equal to xt. That is, error becomes very small. This is the fundamental reason. This is the fundamental, the thumb rule of any control design. Your ultimate aim, if you want to, suppose if you want to disturb a signal, if you want to reject some disturbance, say you have a disturbance at this point, and if you want to reject the disturbance, what you do is you keep this k0 very high. So if you see, if there's a disturbance at this point, then you see output yt is related to the disturbance by this factor, that is 1 divided by 1 plus k0. If I can ensure that k0 is very high, then what we can say is this disturbance can be neglected or this disturbance can be rejected. However, if the disturbance is not at this point but at the sensor, then you have a problem. Then the transfer function or the output and the disturbance relationship would be same as the output input relationship. In that case, your disturbance will not be rejected. So the place where the disturbance is occurring, is very much important for designing your system. So if you are implementing, see in this case, this is a filter problem and we are not using any sensor over here. Whatever problem that you would be dealing with at your undergraduate studies, the unity feedback problem, which is actually a filter problem in which you are not investing in a sensor. Whenever you are placing some sensor at this point in this feedback path, there will be some kind of disturbance over here, and this disturbance is something which is related to the output in a similar manner as input is related with the output. So if you increase the gain, then the disturbance will also be stay in this. Then the disturbance gain factor would become equal to unity, and disturbance will stay in the output. You will not be able to reject that disturbance. So that is a bit of a difficult thing to do, and you would read it in postgraduate studies and all. But this is the main fundamental thing that you have to keep in mind, or the main key takeaway from the questions that I've asked is, the mool mantra for designing any control system is to achieve high gain. That is the reason why you get zero steady state error when you have a PI controller. Okay, or a simple integrator. If you if you are about to track up maybe DC signal, you use a, say suppose a PI controller or a simple integrator, steady state error becomes 0. Why does it become 0? Because the transfer function of this of our integrator is 1 by s, and at DC, at omega equal to 0, the gain becomes infinity. If the gain becomes infinity, that means this term becomes equal to unity. Infinity by infinity it is becoming, so it becomes almost in unity. So if you are tracking a DC signal and you are using a integrator or a PI controller, then the steady state error that you would study, the steady state error becomes 0. That is because at the gain of the PI controller or integrator at s is equal to 0 is infinity. That is the main reason why you get a 0 steady state error for a PI controller. So you guys know what PI controller is? Chaitanya, do you know what PI controller is?
Yes, sir. Proportional plus integrator.
Yeah. So can you tell me what disadvantages it has?
We'll be getting zero steady state error for step input, and that's unity gain. The choice of unity gain will be coming when all the closed loops will consider 0.
I couldn't understand. I'm talking about disadvantage of PI controller.
Disadvantages or advantages?
Disadvantage. I have told
Okay,
you
sorry.
that for tracking a DC signal, PI controller is a very good option because the gain at omega equal to 0 is infinity. As the gain is high, yt becomes equal to xt, so you get a steady state error equal to 0. My next question is, if that is so, should we use a PI controller or should I go for some PID or something else? Is there any disadvantage related to PI controller?
Yeah, deviation will be more with respect to input.
If the steady state error I am saying is equal to 0, then how can you say that the deviation will be more?
It's like this, sir.
Yes.
It's like this.
Phase lag you are talking.
Yeah, in that sense.
See, the phase contributed, the main purpose of a lag compensator is not to provide any, phase to the system. The main purpose of using a lag compensator is to improve the performance characteristics of it. That is to increase the gain or to avoid anti-wind-up phenomena. Anti-wind-up phenomena is not required for you as of now, but there are several other problems which PI controller has. That is what I was asking. So see, the PI controller has the problem that you will face with PI controller is, just let me draw something. So I use this software for drawing. Let me draw this stuff. Discard, okay. So the problem with PI controller that you would be facing is, let me just draw this axis first. This is the magnitude axis. This is the log omega axis. Okay. This is the 20 log axis. Okay. So the problem, say the plant has a Bode magnitude plot like this. This is a plant. This is the magnitude. This is the magnitude plot of the plant that you have. Now, for increasing the gain at DC, these are very low frequencies. So in order to make this gain very high, what you have done is you have introduced a integrator. So what would happen now is the gain, now the plant becomes somewhat like this. right? Right. You are getting my point.
Yes, sir.
So initially you have a plant transfer function like this. Now you have designed a controller which has infinite gain at DC at very small omega. But you see what problem that you have done is, just a minute, I have just a minute. Okay, just let me just show it like this. Put this. Okay. So the plant transfer function, I mean the plant, Bode magnitude block becomes somewhat like this. You have a pole at origin which contributes to the minus 20 dB per decade line, and then over here you have another pole which contributes to minus 40 dB line. Okay. Now see what problem you have created. First problem that you have created is you have shifted, you have shifted your gain crossover frequency from here to here. So your bandwidth has reduced. First problem. Second problem, what you see is you have reduced the gain in the mid frequency zone, in the mid frequency region. Say the frequency less than the gain crossover frequency, or this frequency I am saying is the mid frequency region. You have reduced the gain. So if there is a disturbance of frequency which is lying in between these two, now the disturbance will not be rejected in a fashion that we want that to be rejected. Because you have, by introducing this PI controller, what you have done is you have reduced the gain in the mid frequency region. So what is preferable is instead of using a simple PI controller, what we do is we place a 0 over here. So at DC you are going to have a high gain. But over here, as you are placing a 0, so that pole dB gets cancelled out. It is following the plant characteristics, and at here over you have another pole, and then it again follows the plant characteristics. So what you have done is you have used a lag compensator over here, and by using a lag compensator you are able to overcome this problem of reducing the gain in the mid frequency region. Are you getting my point? Chaitanya, are you getting my point, or Raj?
Yes, sir, I get it.
Okay. So let me give you the last sum for today. This will be the last sum. So these are the Nyquist plot of G1s and G2s that is given to you, and you are asked to find the Nyquist plot of G1s into G2s. So I would give you a few minutes time to solve it, and then we will stop.
B might be okay.
Okay. How are you saying it is B?
For,
Yes.
for second graph, for omega 0 to infinity,
Yes.
so it goes to 90 degree.
Yes.
So it would be K1 K times of S.
It can be S to
All
the
of
power,
the
it can be S to the power 4 also, right?
no.
S to the power 5. S to the power 5.
Yes.
It can be S to the power 5, It can be s whole to the power 4n plus 1.
Yes, sir. So what I want to say that S term comes in numerator in second graph and denominator in first.
So I mean, how can you guarantee that? Say I am saying that this is 1 by s square. Okay, this is sorry 1 by s. This is 1 by s, and this is s whole to the power 5, or maybe this is 1 by s whole to the power 5, and this is s. So how do you justify your point?
Sir, second it becomes s to the power 4.
S whole to the power 5. Yes, s whole to the power 4. Yes, yes. If you multiply that, it will be s to the power 4.
Then for omega 0 the angle is 0 degree,
Yes,
and for infinity it would be 360 degree.
yes.
So,
So
sorry, sir.
so in that case, it would lie either on this line, minus 180 degree line, or at 0 degree line, right?
Yes, yes, sir.
So none of the option would match. So the only option that we have is both of them are equal. S into 1 by s, or s whole to the power 5 into 1 by s whole to the power 5,
The
or s whole to the
most
power 9 into 1 by s whole to the power 9.
the most probable is B is the most
Yes, there is no other option of these two being unequal. So the first thing that you must keep in mind is Nyquist plots are not unique. So two similar functions, two entirely different functions may have similar looking Nyquist plots. Okay, first point that you have to keep in mind. So as Nyquist plots are not unique, so G1s can be 1 by s, or it can be 1 by s whole to the power 5, or 1 by s whole to the power 9, or so on, 1 divided by s whole to the power 4 and plus 1. Same is the case with G2. It can be s or s whole to the power 5, or s whole to the power 9, or it can go up to s whole to the power 4m plus 1. Now one thing that you must keep in mind while you do sums, or whatever you do whenever you solve sums, that this strictly improper function can never occur in practice. Do you know that? You know what strictly proper and strictly improper functions are?
denominator numerator has same power.
Right. So if you see somewhere that numerator polynomial is degree of the numerator polynomial is higher than degree of the denominator polynomial, you must keep in mind that that is not practically realizable system. You cannot realize that system practically because it becomes a non-causal system. So any function which you see is which is a strictly improper transfer function, that is not possible to make such a system. Anyway, so the product of this becomes equal to unity when 4n plus 1 is equal to 4m plus 1. In such a case, it becomes unity, and the entire point maps to a single point in this GSHS plane. If this were not equal, as I have told already, the Nyquist plot will either lie on 0 degree line or in the minus 1 degree line. So the correct option, as you have told, is B. So that would be it for today. I think I would be closing the session now. Okay, so we'll be meeting again on the next Friday. Enjoy the weekend. Till then, bye, man. If you need, I mean, I am uploading these live sessions in the YouTube, in my YouTube channel or somewhere. I mean, one of my YouTube channels. If you want, you can just go through that. If some people were asking the link, let me see if should I give the link, or would you like to, if anybody likes to watch, you can go and watch all those lectures. Where is should I give the link, or you can find it? What will I do? What do you think? Which is a better thing to do?
Sir, I have the link.
You have the link?
Yes, sir.
Okay, okay. then it's okay. Then if anybody wants, you can just share it with others. If anybody wants to, join or something, whatever they want. Okay, man. Then I will be leaving. Okay, bye then.